Have you ever looked up at a fireworks display and wondered exactly how they get those bright, distinct colors? To understand those bursts of red, green, and blue, we have to look at light itself. Light travels as a wave. Think of it like ripples moving across a pond. We measure these waves by looking at the distance from one peak to the next. We call that the wavelength, and how many peaks pass by every second, which is the frequency. Because light always travels at the same constant speed, these two measurements are tied together. If the peaks squeeze closer together, the wavelength gets shorter, and more peaks pass by each second. A shorter wavelength always equals a higher frequency. Our eyes are essentially wave detectors. When a wave with a wide, stretched-out shape hits our eyes, we perceive the color red. When the wave is tight and compressed, we see blue. The specific color you see is completely determined by that exact physical distance between the wave peaks. For a long time, scientists thought light was a perfectly smooth, continuous stream. But physicist Max Planck realized that light energy actually travels in separate, tiny packets. You can think of it less like a steady stream of water from a hose and more like individual drops of rain. When you take a chemical element and heat it up, it gains energy. Eventually, it has to release that energy, and it does so by tossing out these little packets of light. If you heat up strontium, it glows a bright crimson red. Copper glows green. Every element has its own signature glow. This image shows what happens when we take that colored light and pass it through a tool that separates the individual waves. We don't get a smooth, blended rainbow. Instead, we see these sharp, isolated vertical lines of color against a dark background. These distinct lines act like a barcode for an element. Because an atom only ever emits these exact, specific packets of energy, the space inside the atom cannot be random. It must have a rigid, step-by-step structure that forces energy to behave this way. Niels Bohr pictured the atom like a tiny solar system, suggesting electrons circle the center on flat, fixed tracks. When an electron drops down from an outer track to an inner one, it releases an exact packet of colored light. That solar system idea works perfectly for hydrogen, which only has one electron. But the math falls apart as soon as you look at heavier elements. The light barcodes for atoms with 2, 3, or 50 electrons are far too complex to be explained by simple flat circles. Today, we know electrons don't travel on set tracks at all. Instead, they exist in fuzzy, vibrating clouds of probability. We can't know exactly where an electron is at any moment, but we do know the specific three-dimensional regions where they are most likely found. The inside of an atom is built like a sprawling, three-dimensional city. This city is divided into highly specific architectural zones called orbitals. And just like a city, every electron living there has its own exact address. The first part of an electron's address is the principal quantum number. Think of this as the city block. It tells us the overall size and energy level of the main shell. A shell with a value of 1 is a small block close to the center, while 2 and 3 are larger blocks further out. Inside that block, we need to know the shape of the building. This is the angular momentum quantum number. These buildings come in specific geometric shapes, simple spheres, dumbbell shapes, and even complex double dumbbells. Next, we find the exact apartment inside that building. That is the magnetic quantum number. Because we are in a three-dimensional space, a dumbbell-shaped building might be pointing up and down, left and right, or forward and backward. This number tells us exactly which way the apartment faces. Finally, we check the actual occupants of the apartment. Each orbital can only hold 2 electrons at a time. The spin quantum number acts as the roommate agreement. If 2 electrons share the same space, they must rotate in opposite directions to avoid clashing. Block, building, apartment, and roommate. Together, these 4 numbers create a precise, non-overlapping location for every single electron residing within the atom. Now that we know the layout of the city, how do electrons decide where to live? They follow the Aufbau principle. This is a rule stating that electrons will always fill the lowest available energy levels first, starting at the bottom floor and working their way up. The filling order is strictly chronological. The first electrons settle into the lowest spherical shape, the 1s orbital. Once that is full, the next electrons move up to the 2s orbital, and after that they expand into the dumbbell-shaped 2p apartments. They are forced to keep moving up because of the Pauli exclusion principle. This is the strict occupancy limit we mentioned earlier. Under no circumstances can a single orbital hold more than 2 electrons. Because the electrons have to pair up with opposite spins, and because the 2-occupant limit is completely non-negotiable, the atom has no choice. As we look at heavier elements with more and more electrons, the atomic city is forced to build outward into larger, higher energy shells. There is one last rule for moving in, Hund's rule. If an electron has the choice between sharing an apartment or taking an empty one on the exact same floor, it will always choose the empty one. Electrons will spread out into their own individual spaces before they ever agree to pair up. By following these principles, finding the lowest energy, limiting the rooms to 2 occupants, and spreading out when possible, electrons build a highly specific architectural layout for every element on the periodic table. And this brings us back to the lights in the sky. When an atom is blasted with heat, the extra energy temporarily evicts those perfectly arranged electrons. They get knocked out of their normal resting state and pushed up into higher, vacant apartments. They can't stay there. Almost immediately, the electrons drop back down to their proper, rule-abiding addresses. The exact moment they fall, they shed that extra energy by throwing out a specific packet of light. The physical distance of that fall determines the exact color we see. So when you watch those massive bursts of red, green, and blue overhead, you are actually watching trillions of tiny electrons, perfectly following the strict real estate laws of the quantum world.